I have to say that this is a lesson and a video that I thoroughly enjoy doing. Why? Because it deals with division and factorization of polynomials, something finally exciting that doesn't deal with shifting graphs around. Okay, it might help us make graphs, but it's a little bit of algebra, and who can't get excited about algebra? Me. Alright, so recap. What have we been doing previously in these videos? Well, previously we've had examples of questions which has needed us to do polynomial division. Right, now, generally speaking, I suppose the best way to have done that before was jump for our cas. And by the end of this lesson, you may also argue the best way to do this is jump for your cas. But, you know, sometimes doing something by pencil and paper actually gives you a sense of satisfaction, right? So, by doing this, we've been allowed to express complex fractions in a form which we can use to describe a series of transformations of common curves. All right, so we recap and extend the work on polynomial division to show different ways of doing it. Why do we need to divide polynomials, right? People ask me this all the time. Why am I doing this? Well, you're doing this actually because it's critically important to help you solve and do well in an exam and go to university and become an absolute gun in whatever profession you do. But at this moment in time, we found lots of ways of doing stuff for quadratics, right? And we like it to be in a factorized form, which helps us be able to find key points on the graph, turning points, intercepts, depending on how we factorize it. Right, remember, we can use the T method, we can use the quadratic formula, we can use completing the square, or we can use something else, or the cross method. Now, the whole point there was to write a quadratic as a series of linear factors. Now, these things here are linear factors. Why linear? Because we have x to the power of 1. Oh, MG. Now, why do we like to write things as a series of linear factors? If we had 3, we'd have a cubic. Well, generally speaking, when we put them equal to 0, that then allows us to say, well, for a graph here, we know that this has a number of crossing points, which would be at, I don't know, 1, -2, and 3 in this situation. It helps us sketch. And later topic areas of maths allow us to find maximums and minimums and all sorts of different things. So while we have this for quadratics, we don't necessarily have it for cubics, quartics, and quintics. But then we get to polynomial division. Now again, as I've just said there, the end game, do you notice what I did there? End game, Taylor Swift. Keeping it relevant, keeping it real, keeping it hip. So the end game is basically to turn a polynomial, of which this is, degree 3, all right, into a series of linear factors. Now, let's go back to this again. If we were going to solve this, we're going to put this equal to 0, which gives us our factors of x is equal to -3, x is equal to 4, or x is equal to -2. Now, just think about what this actually means. This means that if I put -2 into this equation here, I will get 0 as a result. Likewise, if I put 4 in, or -3, I will get 0 as a result. Now that's actually pretty important. Why? Because this effectively means that if I take x cubed plus x squared minus 14x minus 24 and I divide it by x plus 2, that my remainder will equal 0. All right? It will divide in a whole number of terms, i.e. it's a factor. But it's even better that we don't have to do this division. Although I'm about to show you division, we don't have to. Because if I put -2 into this equation, let's just check. -2 cubed plus -2 squared minus 14 times -2 minus 24. Well, that's -8. That's plus 4. That's plus 28. And that's minus 24. And actually, when we add all those together, we in fact get 0 out. So the great thing is, if I actually want to find out if a number is a factor of this, and so for example, if I wanted to see whether x minus 4 was a factor, no. If I wanted to find out whether x minus 5 was a factor, then if I put x equals 5 into this equation, if the value that comes out, if y ends out being 0, then yes, 5 is a factor. Otherwise, it is not a factor. All right, so one of the ways of actually doing division is through polynomial division. Another one is through what we call synthetic division, and another is using your cas. Now, again, why would you want to divide? Well, given the equation x cubed plus x squared minus 14x minus 24, you might argue, well, how on earth do I turn that into a set of 3 linear factors? Very good question. That's where this information comes in. But to be honest with you, generally speaking, we have to find at least one factor to be able to then move on and factorize this fully. And I'll explain that to you now. So here is polynomial division, which is a bit of a construct, right? So if we are not given an initial factor, we have to find one. So we've been given this polynomial here, and we've got to try and find an initial factor to help us do the division. Because at the moment, I don't know what I'm going to divide this by, right? So, as I say, we might be lucky to be even one, but otherwise we use a process of trial and error. And that trial and error is put an x value of 1, an x value of -1, an x value of 2, an x value of -2, an x value of 3, an x value of -3. Now, if you've got to that point and you still haven't found one, then I'd probably give up or use a different method. But, big hint here, when I'm putting p equals 1 into this equation, what I'm really doing is saying, what will my remainder be when I divide it by x minus 1? Right, so again, by putting p equals 1 in there, it's the same as saying I'm dividing by x minus 1. P equals -1 is the same as dividing it by x plus 1, and so on. So when we put 1 into this equation, we get 1 cubed plus 1 squared minus 14 times 1 minus 24. So that's 1 plus 1 is 2 minus 14 minus 24. Wow, what does that work out to be? 2 minus 14 minus 24. Well, minus 36. Well, that's no good. We're looking for the value to be 0. It isn't 0, so that's not a factor. We put minus 1 in, and what do I get? I get minus 1 cubed plus minus 1 squared minus 14 times minus 1 minus 24. Well, when I work that out, I actually get minus 10. That is not a factor, right? So that's no good. When I put p of 2 in there, and again, we get 2 cubed plus 2 squared minus 14 times 2 minus 24. I actually end up with a minus 40, right? It just seems like I'm getting further away, but actually no, when I put minus 2 in there, I get 0 out. So what I now know is that x equals minus 2 is a factor, which, if we want to write it as a divisor, gives me x plus 2. Having found my first divisor, then, and this is my divisor, and this is my polynomial, we can then lovely start doing our polynomial division. And here is how I do it. Okay, so the first thing is, we are trying to divide x cubed plus x squared minus 14x minus 24 by x plus 2. Okay, are we ready? First thing you do is you always divide this first term by this first term here. Or divide the first term anyway. So you do x cubed divided by x. So x cubed divided by x gives me x squared, and I actually write x squared on top of here. Now, as soon as I've written something on top, I stop, and I'm now going to take this and multiply it by both of these terms here. Why? Well, it's the way you do it basically, but x squared times x gives me x cubed, and x squared times plus 2 gives me 2x squared. And I'm going to subtract them. Why? Well, I'm going to get rid of this term, and then x squared minus 2x squared gives me minus x squared. I always have to have two terms to be able to divide into, and so this term here gets brought down, and I start again. I go x's into x, or minus x squared. So minus x squared divided by x gives me minus x. Minute I've written something on top, I then go back and multiply this by my divisor. So minus x times x gives me minus x squared, which is good, that's what we're expecting. And minus x times minus 2 is minus 2x. Take them away, that now makes those two disappear. And minus 14x minus minus 2x is actually minus 12x. And we drop this down because for some reason we always need two terms, minus 24. And we start again, we do the first term, which is x, in 2 minus 12x. So minus 12x divided by x gives me minus 12. Written something on the top, multiply it by our divisor. So minus 12 times x is minus 12x. And minus 12 times plus 2 is minus 24, which when I take them away gives me 0. Now I am a very happy bunny there. Thank you very much, because I was expecting it to be 0. Why was I expecting it to 0? Because we'd already worked out that that was a factor. And if it's a factor, we're going to get a 0 remainder. So what does that now have to do with anything? Well, what we've actually just proven is our original cubic x cubed plus x squared minus 14x minus 24 can now be split up and written as x plus 2 multiplied by x squared minus x minus 12, right? There is no remainder, and so our fraction or our division can now be written as the divisor multiplied by the quotient. Now the quotient's the thing on the top. Have we finished? No, because remember, we are trying to, as an endgame, get this into 3 sets of brackets, right? Because it's a cubic, should be 3 sets of brackets. We've already got the x plus 2 from here. We now need to come up with, hold on a moment, buddy boy, we know that that is a quadratic. So taking this out and dealing with it on its own, we get x squared minus x minus 12. Do my t method of minus 12, so we get 1 and minus 12, 2 and minus 6, 3 and minus 4. That seems to be the one we want. So x squared plus 3x minus 4x minus 12. Factor pairs gives me x plus 3. Take out minus 4 gives me x plus 3. And factorize again gives me x plus 3, x minus 4. And ladies and gentlemen, x plus 3 and x minus 4. That is my fully factorized form for my cubic using polynomial division. Now I have to say, this is something that requires practice. There's no two ways about it. You get a minus sign in the wrong place, or you don't add things properly, you're going to hit all sorts of problems. But it's certainly one way of doing it. And this tends to work really well when we have non-linear functions. So if I was ever doing x cubed into x to the 5 minus 4x to the 4 plus 3x to the 3 minus 2x squared plus x plus 4, wow, that was long. This method, this polynomial division, actually works brilliantly here. The method I'm about to show you is not good with that, but let's move on to synthetic division. All right, now I personally love this, but I have no idea why it works. All right, I'm sure I do. It's just the video would stretch to about 8.5 hours. All right, again, you need to find a factor this work, but once you have, it's a breeze. And you're wondering, why on earth is Judge Judy here? Well, don't judge me about the fact that there are things I sometimes don't know how works. I'm not overly sure why quantum physics works, but I'm more than happy to just accept that it does. All right, so let's go back to our original question, which is this one here. And I'm going to turn around and say, well, we already know that x equals 4 is a factor. And this is what you do. And this is absolutely amazing. Number 1, so step 1, we're going to work down the steps here. Write down the coefficients of my original polynomial. So I'm going to write down 1 for x squared, 1 for x cubed, 1 for x squared, minus 14 for the x, and minus 24. I'm going to draw a line, and I'm going to draw another line here, and then I'm going to write down the value of 4 here. Why? Because this here is my factor. We know that one of these is already a factor. Now, this is where the funky bits. You always have to start with a number down the bottom under here. Why? Because you just do. The reason being is, having written down this first number here, we take it and we multiply it by this value here. And the trick is, anytime you write a number in the bottom column, you multiply it by the factor and you write the response here. Okay, right, so 1 times 4 is 4. Anytime you write a number in this column, that row, you add them together. So 1 plus 4 gives me 5. I've written a number in the bottom row, so I have to multiply that by my factor. So 5 times 4 gives me 20. I've written something there. We add them together. Minus 14 plus 20 gives me 6. 6 times 4, multiply them together, gives me 24. And then we add them together to give me 0. And OMG, that is so easy. But what do the values mean? Well, this last value here is always our remainder. And in a moment, we'll come back to something called the remainder theorem. Now, because our remainder is equal to 0, we know that x minus 4 or x equals 4 is a factor, which is good because we already knew that. But what do these 1, 5, and 6 mean? Well, interestingly, that is the next part of our quadratic. So we already know that x minus 4 is a factor. We take the 1, and that now becomes x squared. Why? Well, this one originally was x cubed. This one was for our x squared term. This, you just take 1 off the degree. So that becomes our x squared term. This becomes our x term. And this becomes our constant. And so we get 1x squared plus 5x plus 6. So, using our t method, we get x squared plus 5x plus 6. So let's draw our t. We've got a 6. So that's 1 and 6, 2 and 3. That seems to work for me. Thank you very much. We have x squared plus 2x plus 3x plus 6. Factorize our pairs. Move my screen up to give me a bit of real estate. X plus 2. Take out plus 3 there. We get x plus 2, which is good. We have a pair of stuff, a pair of terms that actually have the same thing in it. So we get x plus 2, x plus 3, and so we get x minus 4, x plus 2, and x plus 3, which I'm pretty sure was what we got before. I don't know about you, but synthetic division seems to be a lot easier. And then we get to this remainder theorem, and I've already explained this to ad nauseum. Remember, these were the examples we did before. When we put 1 into this equation, we ended up with negative 36, i.e., dividing by x minus 1 does not give 0 as an answer. In fact, it gives negative 36 as an answer. When we put minus 1 in, which is the same as x plus 1, so if we were to divide this on my CAS calculator by x plus 1, I'd end up with a remainder of minus 10 and minus 40. It's only when it's 0 is it a factor. And funnily enough then, so the reason we talk about the remainder theorem is when we divide something that does not give us a 0 value, we say that it has a remainder. So here's an example. Find the remainder when x cubed plus x squared minus 14x minus 24 is divided by 2x minus 1. Well, if we know that 2x minus 1 can be arranged into 2x is equal to 1, x is equal to half. So what we're saying is, well, let's put a half into this and see what happens. Right, so what do we get? Find the remainder when, so we get 1/2 cubed plus 1/2 squared minus 14 lots of a half minus 24. Well, 1/2 cubed is an eighth plus a quarter minus 7 minus 24. Now, I don't know about you. I don't need to go too further to realize that that is not going to equal 0, right? So if I wanted to, or if the question I wanted to, and for time I'm running out of, then we'd actually write down what the physical remainder of that was. But the good thing is I would now know that that is not a remainder. And oh no, please not more. Broken record time. What is the factor theorem? Oh, yawn. This time we know what the factor is, all right? So basically, when you divide something by something else, if the value comes out as 0, it's a factor, right? So again, we come back to this idea now of forwards and backwards. We've learned to do this forwards. Now let's look at a great example of doing it backwards. This time, we're given a polynomial with some values missing. We know it has two factors of x plus 1 and x minus 3. Now what that means is, if you remember, that if I now do the polynomial and put in the value of negative 1, out comes the value of 0. And if I put in to my polynomial 3, out will come 0. And in that, hopefully that gives you the way forward. All right, how? Well, let's put minus 1 in. So we get minus 1 to the power of 4 minus a to the power of minus 1 cubed minus 7 lots of negative squared 1 squared plus bx plus 24. When I put that in, I get 0 out. And when I put 3 in, so 3 to the power of 4 minus a, 3 to the power of 3 minus 7, 3 squared plus 3b plus 24 equals 0. Now, what have I just noticed there? Actually, that x value could have been replaced to become b times negative 1. Having got that information, what would I do now? I would simplify. And then I would put it into my CAS, and I would solve to find my values. All right, I'm going to leave that for you guys to do. But almost at the end, sums and differences of cubes. Basically, memorize these. They are incredibly important. Where we had, a squared minus b squared is equal to a plus b, and a minus b. Right, the difference of two squares, which can be rewritten as this, which is a fabulously important result. The same is true of cubics. And my advice to you is make sure that you put your cubics in your notebook or just memorize them. Now, whereas we can't write a squared plus b squared is equal to, a plus b, that makes no sense. There's no equivalent. For cubics, there actually is. All right, so you can split x cubed plus a cubed into something here. Solving polynomials, as we've done previously when we want to solve polynomials, if I have 3 linear roots and put them equal to 0, then we use null factor law to find the situation, and I don't need to explain any more on that until we get to this fabulously, confusingly bizarre rational root theorem. Now, the rational root theorem states that an equation can have 0 roots, or the roots found by basically doing this, the factors of this, divided by the factors of this. And it suggests somewhere in this, and there's a lot of maths behind this, there will be a number of them that will give you a 0 root. Now, this is the way we use the rational root theorem. And again, it's a construct. It's just a series of things, and it's not particularly nice. But look at the last digit, and it's 5. So the best way to do this is to draw a table. And I'm going to put the value 5 there and 3 there, because we are going to end up dividing all of these different factors against each other. So the factors of 5 are plus or minus 1 and plus or minus 5. I know this sounds bizarre, but you'd be plus or minus 3, plus or minus 1, and plus or minus 3. And somewhere in here, right, and there are currently 4 possibilities, there may be up to 3 factors. Why? Because if you remember, with a cubic, we may have a situation where there are 3 crossing points, but just as likely, there might be a situation where there's only 1. So that's why we say up to 3 factors. How do we find them? Well, we take each of the top values and divide them by each of the bottom values to give us our 4 factors. So we have plus or minus 1 divided by plus or minus 1, plus or minus 1 divided by plus or minus 3, plus or minus 5 divided by plus or minus 1, plus or minus 5 divided by plus or minus 3. Oy. So what does that now mean? Well, generally speaking, I can ignore the plus or minuses on the bottom. And so it says I could end up with plus or minus 1, plus or minus 1/3, plus or minus 5, and plus or minus 5 on 3. Now, you're going to say, well, hold on a moment. There's 1, 2, 3, 4, 5, 6, 7, 8 now. There are 8 possible outcomes. Yeah, 8 outcomes, not 4. What was I thinking? I was just being lucky. So there are 8 possible outcomes there. How do we know which one of those will give me a factor? Well, remember, to find out whether it's a factor, we have to substitute each of these values into this equation here and find out which one comes out 0. So we would quite literally need to put positive 1 into that equation and see what comes out. Then we would put negative 1 into the equation and see what comes out. Then you'd move to this third and you'd put 1 positive 1/3 into the equation. And then you'd put negative 1/3 into the equation. And then you'd put, you see where this is going? Positive 5 and negative 5 and positive 5 on 3 and negative 5 on 3. Now, if you're really lucky, one of these will turn out to have a value of 0, and you only need to find one of them. Why? Well, once you found one of them, you can then use your synthetic division to find all the others. Okay? Wow. Now, while we ended up here with 8 different possibilities, imagine what would happen if you had the n numbers as 18 and the leading is 6. 18 has 1, 2, 3, 6, 9, and 18. 6, 1, 2, 3. You now divide, so that's, you're going to end up with 1, 2, 3, 4, 8, 12, 16, 20, 24. You will end up with 48 different solutions. Ouch. Fingers crossed if this ever came up in an exam, and I can't imagine for the life of me it will, that you get something drop out really, really quickly. All right, so there we go. What was this all about? It was all about polynomials. It was about factorization and division. Why? The final point to all of this was we are trying to separate things into a series of linear factors that I can then theoretically put equal to 0 to solve and find my x-axis intercepts. Right, this lesson's been long enough. I look forward to seeing you next time.